Hey guys, it's your boy back with another video. Alright, let's get right into it. This video is about rotational velocity and acceleration of rigid bodies. Practice problems by yours truly, Jan Philippe Ang. Alright, getting right into it for our first problem. An airplane propeller is rotating at 1860 RPM or revolutions per minute. Now, what we have to do is compute for the propeller's angular velocity in radians and how many seconds does it take for the propeller to turn through 40 degrees. So right here we have our propeller, little diagram. So getting into our solution. So for our angular velocity, forgive me, that's supposed to be an omega. So it's 1860 revolutions per minute. So we are required to look for omega in radians per second, which is our angular velocity, and time at 40 degrees. So the first thing we did here is cancel out the minutes. So we have 1860 over 1 minute times 1 minute over 60. So the minutes cancel out. You have 31 revolutions per second. Now next we have to cancel the revolutions and replace it with radians. So to do this, we multiply it by 2 pi radians over 1 revolution, which gives us 62 pi radians over seconds. So if we multiply that out, we will be getting our final answer of angular velocity, or omega, equals 194.79 radians per second. So next we have to look for time. So we're given 40 degrees. So the first thing we have to do here is multiply it by pi over 180. So this will give you radians instead of degrees, which is 2 pi over 9. Next, we have our formula for angular velocity, d theta over dt. So if we manipulate that a bit, we could get our formula for time, and we could plug in everything we already have. So we have 2 pi over 9 divided by 194.79, which will give you a time of 3.58 times 10 to negative 3 seconds. All right, so that was pretty simple. So for our next problem, we have an electric fan. It's turned off, and its angular velocity decreases uniformly from 550 revolutions per minute to 210 revolutions per minute in 4.40 seconds. So we are looking for the following. Find the angular acceleration in revolutions per second squared and the number of revolutions made by the motor in the 4.40 second interval. Then we have to look for how many more seconds are required for the fan to come to rest if the angular acceleration remains constant at the value calculated in part A. Alright, getting into our solution right here, we have a given of an initial angular velocity of 550 revolutions per minute, a time of 4.40 seconds, and a final angular velocity of 210 revolutions per minute. So we are looking for alpha, which is our angular acceleration, and the number of revolutions made in 4 seconds. And then we go on to look for t until the fan comes to rest. So first thing we do is use the formula for alpha, which is change in angular velocity over change in time. Now, as you can see, it's kind of tricky. We are given revolutions per minute, so we want to turn that into revolutions per second. So if you look at our solution, we divided by 60. So 210 divided by 60 minus 550 divided by 60, all over 4.40 minus 0, given that our starting time is 0, which will give us a negative 1.29 revolutions per second squared. Now, that is correct because it is slowing down, it is decelerating. So, for our theta, we are looking for change in theta, how many revolutions made in that 4.40 second interval, rather. So, we use the kinematic equations from linear to rotational. So we have theta equals 1/2 times initial angular velocity plus final angular velocity times time. So once again, we convert it to revolutions per second, dividing by 60. And then we plug it into that equation, and it'll give us 27.87 revolutions. So we already have two of our answers. We look for our time next. So once again, we use one of the kinematic equations. So we have final angular velocity equals initial angular velocity plus angular acceleration times time. So if you manipulate that a little bit, you'll get our equation here. And note that we are coming to rest. So our final angular velocity is 0. So plug in everything else, plug in the acceleration we calculated for earlier, and you will get 2.842 seconds. That is 2.842 seconds. All right, almost there. So this is our last problem. So, in a charming 19th century hotel, an old-style elevator is connected to a counterweight by a cable that passes over a rotating disc that is 3 meters in diameter. The elevator is raised and lowered by turning the disc, and the cable does not slip on the rim of the disc but turns with it. So, how many RPM must the disc turn to raise the elevator at 20 centimeters per second? To start the elevator moving, it must be accelerated at 1/8 g. What must be the angular acceleration of the disc in radians over seconds squared? Lastly, through what angle in radians and degrees has the disc turned when it has raised the elevator 3.3 meters between floors? So here we have our little diagram, and note that it is similar to an Atwood's machine. So getting into our solution, we have right here our given. You have seen the sketch earlier. And we have a radius of 1.5 meters, which is half of 3 meter diameter. Then we have our acceleration required, which is 1/8 g. Now we are looking for angular velocity for a velocity of the elevator to equal 20 centimeters per second in revolutions per minute. So it's expressed in revolutions per minute. Then we have alpha, angular acceleration, in radians per second squared. Lastly, we are looking for the theta when the elevator is raised 3.30 meters. So for our solution, we're going to start off by changing it to the right measurements. So we have 20 centimeters over 1 second times 1 meter over 100 centimeters. This will cancel out the centimeters and then multiply by 60 seconds over 1 minute, so we can express the answer in RPM, which gives you 12. Now we have omega equals V over R. Now this equation is the equation that we use to relate linear motion to rotational motion. So we already have our V, which is the velocity of the elevator, which is 12 RPM, over our radius, 1.5 meters, which will give you a final answer of an angular velocity of 8 RPM. Now we have to look for our alpha. Now once again, this is another equation that relates angular and linear. So we have angular acceleration equals acceleration over radius. So it was stated earlier that it requires a 1/8 g. So g here is gravity, not grams, all right? So 9.8 over 8, which is our 1/8 g, divided by our radius of 1.5. So that'll give you an alpha that is equal to 0.817 meters per second squared. Lastly, we have our theta equals S over R. Now S is the angle subtended, right? Now since it was stated earlier that the cable does not slip, you can surmise that the amount of the distance that the elevator rises is the same distance that the angle changes or shifts. So we express our S as 3.30, and once again plug in our R, which will give us 2.2 radians as our theta. Now recall earlier, we need to express this in degrees as well. So simple enough, multiply our 2.2 radians by 180 over pi, and that will give you a cool answer of 126.05 degrees. All right, so that's all our problems for today. Now, if you want to practice more problems, if you want to read more about physics, be sure to check out University Physics with Modern Physics, Volume 1, and you know what? Volume 2 by Young and Friedman. Thank you for listening. This has been Yan Ang, and don't forget to like and subscribe. Thank you.